Hi guys, thanks for the introduction. Sorry. Yeah, as Nitin said already, my name is Christoph, and I'm very excited that I can speak today about deep learning and especially deep learning in the browser. It's really, really exciting, so I hope I can share this passion with you. Just very little about me. As Nitin said already, I'm working at T-Mobile in Austria, in Vienna. But the work that I showed today is mostly based on my master's in visual computing, also at Vienna. It's mostly based on ConvNetJS, but there is a lot of stuff going on. So since we agreed on the name of the presentation and everything, a lot of things have happened. So I've also included some other more cool demos that are not based on ConvNetJS, but more recent technologies. Yeah, so most of the things you see are based on Cafe.js. So it's a framework for running Cafe models in the browser. Yeah, so I also do a lot of visualization. I have 2 books about data visualization, and I also organize the Kaggle meetup in Vienna. So when you're in Vienna one day, you should join the Kaggle meetup. It's really nice. So what will I speak about today? First of all, I want to tell you why actually running a deep learning model in JavaScript makes sense. The second, yeah, it's complicated, let's say. The second thing is I want to bring you guys all on the same page. So I will give a very brief introduction to neural nets and deep learning. It's very, very simple. I use also one equation, so I hope I hope that's okay for you. Yeah, trust me, it's going to be simple. And if somebody completely has no idea what's going on, just raise your hand and I will, yeah, either speed up or you slow down. Third, of course, I will show you the transition, state of the art of running deep learning models in the browser, training them, and so on, and what actually powers JavaScript to do all this. And then we see more demos. Yeah, so that's actually the main reason why we want to do this. Why run JavaScript? Why run deep learning models in JavaScript? Is it just to satisfy you, or are there any practical applications? And it started like this. You just as a proof of concept to see what is actually possible, but there is much, much more. So first of all, I'm super excited about the browser, right? What happened in the past years, where the browser is today, it's such an amazing platform, and it makes every technology accessible to anyone on almost any device once it runs in the browser. So that's really cool. Once it's JavaScript, you can also run it server-side, which, yeah, it's also nice. The most thing I liked about actually my whole journey in deep learning was once I was in JavaScript, I could just use the Chrome debugger, right, and put a breakpoint in the backward pass or in the forward pass and see the activations and see the gradients. So it was an amazing tool, or it is an amazing tool for debugging. And of course, I love interactive visualizations. And once you're in the browser, you can just easily visualize everything. So that's a bit more for education and training and learning, but there might also be some practical applications. These are actually, I have not seen any company implemented one of those yet, but they are possible in theory, so it could be done. So first, you have access to a lot of data, right? You're on the client, you run in the browser, so actually you could just use the cursor movement of the browser of the laptop, or use the typing speed of the keyboard to train evaluate the model and find out the gender or the age of the person that uses a laptop, something like this. Like you have access to a lot of data. You could do massive parallelization. Imagine that you could run a backward pass on any device that uses your website. Like imagine you're at the scale of Facebook or Google and you embed this in your website somehow. I mean, that's really massive. And last is also you can do really cool things for applications that require privacy. For example, imagine your Proton Mail and you want to build a feature that gives you smart reply in Proton Mail in the browser. So you could just apply the model on the text in the browser, and it doesn't have to leave the browser at all. So yeah, I think that's wonderful, and I'm very excited, and I think we will see some of these applications very soon. So yeah, here a few screenshots actually. So I forgot to say, everything is running in the browser, like from the presentation to the demos. All the screenshots that you see are made in the browser. The slides are also available to you guys, so you can run the same things on your smartphone or on your browser actually right now. So let me go back, you may saw it. So here's the link, it's bit.li Jason 2017 -dl. So if you want to run any of these demos on your phone, yeah, you can do it. So let's give you a quick taste how this looks like. For example, you take an image, right? Everything is in the browser. Let's make it a little bit bigger. And here you see the model structure that is used for this. It's pre-trained on ImageNet, and then you hit classify, for example, in here, and then you classify it. You get the result of the ImageNet classification. You can see all the layers, right? Everything that we saw before in the previous talks, but now everything runs in the browser. If you want to know what's going on, just put the breakpoint in some, if you're excited about these fire modules, maybe just put the breakpoint somewhere and see what's going on. So here on the right is a screenshot of the same thing running on the phone. That's a bit boring. Yeah. So, and because it runs everywhere, because it runs in JavaScript and in the browser, integration into other tools that built on JavaScript is also simple. Like imagine you can prototype now apps in Electron, for example, and you can just add deep learning capabilities. I think that's really cool. Or to JavaScript chatbots, or to Google extensions or so on. Yeah, so this is the debugging feature. I told this already. Some cool interactive visualizations. So this is a screenshot to the demo from ConvNetJS, where you can actually train a model in the browser. I will show it later. So now let's jump to the intro to neural nets. So what is the technology that powers all these things? And I want to build with you a classifier that separates either pedestrians or cyclists. Let's assume you build a self-driving car algorithm and you want to classify if someone is a pedestrian or a cyclist. And for this we are going to use supervised classification. So yeah, obviously we need to collect the training set, right? So we go with our car and we take some pictures of people, and then we annotate the training set. So we have the green labels, which are pedestrians, and the red, which are cyclists. And then we want to find the function, right, that shows us, that returns us the class of the label. So what we do, how we're going to do it, is we draw a random separation line to separate these two classes. So it's random, so it's very bad. You can see here, it doesn't really separate these classes at all, but it's a good way to start. So now I'm going to tell you about the separation line because it's somehow important. And this is the equation that I promised you. And it's indeed very scary, yeah. It's the line equation, yeah, no surprise. Well, it's multidimensional, so it's a hyperplane in theory, but it's okay. It looks like a line equation, so it is a line equation. You have some weights W, right? You have a bias B. This is the things that you assigned random before, and you have some input data, and what you get out from this function actually is a line equation, and if you put the input data inside the equation, you actually get the distance from the line. So, yeah, that's very cool, and a great place to start, actually. I also give you the schematics of this, because this is what you usually see when you see deep learning. You see a lot of these schematics. So this is how the line equation looks like in schematics. You have the input that goes in, you have the W and the weights and the bias, and you get something out. So before you saw, X is, actually we don't have just one dimension, so it's multidimensional. So make here two inputs, and we optimize a little bit, so we remove the bias, so we can, we could append a 1 to the input, and then the bias could be included in the weights. So like this, it looks a little bit simpler, and we can continue stacking them together. So now we know this is a line equation, and we know that it returns you the distance to the line. Actually, if it's on one side of the line, it's greater than 0, and on the other it's less than 0. So now we want the function that actually just not gives you the distance to the line, but the actual class. So what we do is we need an activation function. An activation function maps actually this value to the side of the line. So it gives you either +1 or -1, for example. And there are different activation functions that do like slightly different things, but the sense is actually the same. So the activation function looks like this. It's a simple step function, for example, and it maps our values to -1 and 1. So now we simplify this again a little bit. We make a circle, and this is what we call a neuron. So this is like will be the building block of everything that we use beyond this point. So here we have this +1 and -1, and now we want to know. So this random line, how good is it actually? We can see it's not very good, but we need a measure to measure how good it is. And so what we do is, we somehow need to find out the ones that are on the right side and the ones that are on the wrong side. And we do this, this true jumped a little bit, but we do this by comparing the output, the y, to the ground truth data that we collected before. And we compare these two, and we compute an error or a loss. And this error tells us you are either good or you're bad, and it tells us also how good and how bad you are. And we use this error actually afterwards to use a technology called gradient descent to update the weights iteratively. So by updating the weights, we always shift the line closer to the actual where you might think that it should be, so that it minimizes like the wrongly classified samples. And so now we see actually it's good, but there are still a few that are still on the wrong side. And also we want to get this somehow. But we cannot do this with a single line just, right? So what we do, we take 2 lines. Okay, so with 2 lines, now you can see the blue line and the yellow line, and this +1 and -1. And now we could see actually that it could work out. This looks like this now. So we have 2 outputs. But with 2 outputs, we still have to combine the outputs somehow to actually get to this red class. And combining the output looks like this. We actually want this black thing. So we want the +1 if it's in these 3 quarters, or we want the -1 if it's in this quarter. And we do this actually by stacking another layer into it. And that's very important. So if you look at this picture again, another layer means a combination of features from the previous layer to, it's a little bit more complex feature. Right now it's 2-dimensional. Before it was just either this side or the other side. Now it's a region. And that will be very important afterwards. So we remember we have stacked neurons into layers. The layers are actually just line equations. We have activation functions, and we output a class score in the end. And then we have also this optimization phase, right, where we compute an error, and we go back and updates the weights from before. And actually the first thing is called inference or forward pass, and the other thing is called training or also back propagation, for example. It looks like this. So inference, you go through the graph in the front, and back you go into the back. So there's a cool demo doing exactly what I showed right now. So it's playground.tensorflow.org. It gives you a neural net in the browser. It gives you some input data here, and you can have a few settings. So how many layers do you want? How many neurons in the layer do you want? And then you can hit play, and you can train the whole thing, and you can see it converges very quickly, and builds a model that can fit this training data. So you can take also more complex training classes, right? And then you can continue and see also the output of this. So I recommend you to play around with this to understand what actually I just previously said about the introduction to neural nets. So let's continue. Now we are at neural nets, right? But we are not at deep learning yet. So what are actually the ingredients to go from neural nets to deep learning? Well, it's we will have a lot more data. So a lot more data also requires a little bit more efficient, efficient layer structures. Because we'll see this later, if the input gets very large and then the number of parameters gets very large. So the answer to this is something called convolutional layers, and I will explain it in a second. And there is also something like pooling layers and a lot of other layers that help you to be more efficient. And with more efficiency comes deeper models and also wider models and new model structures and so on. So what is the theory behind convolutional layers? So if we see here on the left side, if we are high dimensional, so an input image, if you have image data, right, you can see typical dimensions of an image that are used in ImageNet, for example. So if you use 3 times 227 times 227 high dimensional space, I mean, it's quite high. And if you have only 2 neurons, the number of parameters is this times 2, right, plus the bias. So that can grow very, very large. Imagine if you have, not 1 neuron, but 1,000 neurons, that can grow very large. And the idea of convolutional layers is actually to share the weights. So you don't run this computation using different weights for all the input. You use the same weights between these inputs. So you run this in sequence, and then you sum up the values. And with this, you actually share a lot of weights. Because now you only have 2 times 2 weights in this example. The nice thing about this is that these weights, these convolutions, they are actually filters. Like in images, they work like edge detectors and blob detectors and so on. And so this is in the very early layers, and throughout the layers in the network, the filters get more complex and detect more complex features. So I will quickly show you this example. This is training a neural net, deep net in the browser using ConvNetJS on the MNIST dataset. MNIST is a handwritten digits dataset, and you can see here that you can even change the network model, and here is the training running, and then you can see the activation throughout the layers, and you can see here the predictions on the unseen test set. And you can see after a few iterations, this thing gets quite good with only a few layers. So there's like, I think 2 convolution and 2 pool layers, and you can see how they look like. So these are actually the filters. So they look like this. And applied this filter, you can see actually black and white on the side. So this is like an edge detector, right? So yeah. On the one side, it's very efficient. On the other side, it's very nice because it gives you this filter property. Okay, let's stop this. So I said the models are getting deeper and deeper. This was very horrible for me to see that every year the model's going deeper and deeper. The number of parameters are going up and up. So we started in 2012, and the model had 60 million parameters, and it was 240 megabytes big. And then there was VGG, and it was even bigger. And I wanted to run it somehow in the browser. I was said like, that's never going to work. Fortunately, there's also some effort going into making the model smaller, not necessarily. So they even make it deeper, but they can also make it smaller at the same time by using some efficient structures. For example, the GoogleNet architecture, it uses only 7 million parameters. Compared to 60 million, that's quite a good improvement. And also the error on the ImageNet classification test set, it's much smaller. So that's very nice. And then there's also the SqueezeNet architecture recently, which goes even further. And so you have the full model at like 5 megabyte. And if you can still improve this with compression techniques, then you need customized inference engines, but still you could improve it further. To explore these models and what is behind, you can also just click on the link and open the models in the visualization. So let's make this a little bit smaller. So here you get a compact view, how I call it. So it's more like a module-wise view. So you see here these inception models that we also heard before. And you can actually here click on the button to see what's behind these modules, and then you see actually that this is a wide model that consists of certain filters that are applied on the same input, and then the filter activations are just stacked together in the concat layer. Yeah, so you can explore this, can really understand what's going on in here. Right. So yeah, so this is a really cool demo, the Deep Dream demo. It's you for sure have seen it a couple of years ago, so it was quite popular. Why I like it is because this demo really shows you how the depth of a network is detecting features at different levels. And the idea behind this demo is that you replace the loss functions in the end with just the weights of the last layer, like the distance to this line, if you remember. And what you want to be is actually, you want to find this line. So you want to find actually the separation line in this certain layer. So you go forward to this layer, and then you compute the error, which is just actually the weights of this layer, and then you back propagate this error back. And this gives you these wonderful images. So we start with a very early layer. We get very linear looking features. And as we increase the depth of the layers, we get more complex looking features. And you can see here, we have already circles, and kind of, some geometrical shapes. And here is something in the very end. You can see it looks like houses and so on. It looks like a city. And I picked here out a picture that is using a layer somewhere in the middle of GoogleNet. And you can see that the features are more like eyes, and it's connecting eyes and hair and so on. Also, this you can see this running in the browser, right? Yeah, it takes a little bit. So this model, as I said before, is 30 megabytes big, so it takes a little bit. This is one of the few demos that runs completely in web workers. So it's running in a separate task than the browser. So this is also really cool. So you can see that we have here like 4 octaves, and every octave we make the size, we increase the size, and then we try to interpolate the lines in between with more features. Yeah, so turn this off. Okay, and what is the good news about this is, so this uses cafe models, and there are a ton of models, of pre-trained models available. Pre-trained on different data sets for different tasks, for different frameworks. So there are models available for Cafe, there are models available for Keras or TensorFlow or for Torch or for all the other frameworks, basically. And you can find models for classification, for segmentation, localization, detection, word embeddings, face detection, or whatever. You can just go to the links and see there's a long list of models that are trained on different data sets for different purpose. And right, so yeah, you can find all these models, and the nice thing is that the idea of most of the frameworks in JavaScript that I will show afterwards, the idea is to make it as simple as possible for you to run the model in the browser. So you just download, like literally go download the Cafe model, and I think you will see in a couple of days that you can just load this one model, no pre-processing, no compiling, directly in JavaScript and run it there, which is actually pretty cool, I must say. So how it's done right now? Right now, you have to compile the binary model before and split it into different blobs. Because when I started with the library, I started with AlexNet, and it was 240 megabytes. And I started with JSON, which is apparently an amazing format for big data, like this. No, it's horrible. So I couldn't parse it, so I had to chop it down in pieces, and yeah, until I read out array buffers, but that's another story. So, so the summary of this deep learning introduction is that because of the weight sharing, we should use mostly convolutional layers. These convolutional layers, they act like filters, and the deeper the networks go, the more complex features these filters detect. And so they start with edge detectors, then it's more shapes, and then it's eyes and cities and what we've seen before. And yeah, many models are available, and also all the cafe like the models included in Cafe, so they're like 5 or 6. They're under a license for unrestricted use. And all the other models published, they have usually certain license agreements, but it's most often it's open source licenses and available for commercial use also. So that's very great. So you can just download, put it in your application, and run it. That's really nice. So yeah, this is about JavaScript, right? So you've seen some demos, and so if you're a JavaScript developer and you're excited what is the technology behind, I have one slide for you here. So actually it's really fascinating because JavaScript has something called typed arrays, and typed arrays is supported in every major browser, also on the mobile phones. That's why these demos work on the mobile. And it has something called array buffers, which lets you interact directly on a chunk of binary data in memory. And this makes it really, really fast, to store large arrays, to iterate over arrays, to multiply arrays, and so on. It also has great GPU support with WebGL, which is nice. So you can even have GPU accelerated applications. I will show some of them later. And you can do multi-threading in web workers. We saw this in the Deep Dream demo. It works also like Charm. And what I like the most, actually, is that you have such a rich APIs, right? You have access to the webcam. You have access to audio. You have access to MIDI. You can parse sound. You can generate sound. There's lots of cool, complex, sound processors in JavaScript. That's really exciting. I mean, you can build really nice applications, really nice demos just in the browser with these tools. There are a few challenges, though. One that I explained was the network load before. So had the memory consumption, loading 240 megabyte of AlexNet, that doesn't make your clients very happy. So as the model size decreases, though, it's getting possible. Another thing I have to mention is that there's no CUDA support in the browser, which is, it's very, very sad. So you have to, transform your tensors into textures, and then have to run the computations in the shaders. So it's a bit annoying. So, but if you use small models, it's actually fine. So here's a list of models that is available today. So starting with ConvNetJS, which was actually is the oldest, and it is somehow the foundation and showed what is possible. It actually emphasized that we could do both inference and backprop in the browser. So it implemented this both in only CPU. And it also let you export and import models in JSON files, so and the trained models, and to load them. So actually, if you go to the Stanford website of the neural networks course, there's a neural net running in the browser in the header, predicting classes. So that was built for showcasing this. Yeah, then I developed a Café.js to run deep learning pre-trained models in the browser. But because I built on top of ConvNetJS, so most of the work was done by in ConvNetJS, I just added a few things. And so with this, I could also do inference and backprop, which was, for example, necessary for the Deep Dream demo that you saw before. Though I wanted to make this as easy as possible to port Café models, and there's a few tweaks in how to compute the filter sizes, and this is only specific to Café, so it's only, it supports like only Café models. Then there's a more recent library, which is Keras.js. It's really nice, I need to say. It focuses on GPU support, but only inference. So you can do really, really nice things. Inference only, so you have an image and you do something with it, and I can show some demos also afterwards. And which has compatibility for Keras models. And then recently, so 2 guys from Google, they developed DeepLearn.js, which does all the things. And it gives you Keras and TensorFlow compatibility, and there'll be very soon Café support, I think so. And yeah, it's a really nice library. It's very how to say, it gives you more the foundation, right? So you don't have to write the shaders yourself. It gives you more the access to the technology behind, and then you can build on top of it. Yeah, but it's really cool. Yeah. So, and we still have a couple of minutes for demos, so let's jump right in. So this is a really nice demo implemented by a lot of people, not me, unfortunately, but it's very cool, so I will show it to you. It does actually basically the exact same thing that I showed you before. Like before we saw this pedestrian cyclist detection, and now we will make like a little bit more sophisticated. We make like a cheering, laughing, and sad face detection. And we train it completely in the browser, you know, just using the webcam. And let's see, let's hope that it will work. So this is how it looks like. It's a very simple interface, and then you have these three classes. You have the green class, you have the purple class, and the orange class, and then you can map these classes to GIFs. So let's make some cheering. Yeah, this guy looks good. It's this guy. So let's make some laughing. Let's use this guy. And a sad face. Oh, this looks perfect. So, right, okay, so, you know, and now we can just press the button, and unfortunately have to hold the mouse. So it could be implemented a little bit better, but so I have to hold the mouse while I train it. So I can use only one hand for cheering, but I will start, and you will see that the thing will collect the training data. You can see the number of samples that it's used for training. So now I cheer, and the guy is applauding me. Oh, that's fantastic. So now we can continue with the laughing. So I have to smile a little bit. I have to shake a little bit so that it's detecting me, and it's collecting the training samples. So if I laugh, yeah, and I cheer, all right, that's nice. So we still have the sad face, right? So we have one more. Well, it seems yeah, so well, not too so it always thinks I'm super happy, which is nice. Okay, so this also has, you know, sound support and speech, so it's really cool. I strongly recommend you to check it out. It doesn't work very well on mobile, so it's very experimental on mobile, but yeah, it just works completely in the browser. It's completely astonishing. Yeah, that's teachable machine. So also you have seen fast neural style transfer. I'm pretty sure everyone has seen this, but there's a cool demo here running also entirely in the browser. You know, this you can just again use the webcam, take a picture, and then use a style, and you transfer your style to this picture, entirely in the browser, which is unbelievable. I find this really nice. All right, so what else is there? So there's models working on text. So there's, for example, sentiment classification. That's also really cool demo. So, but you know, text for me. So I always use images, because images is super nice. It's visual, you know, and you can understand what's going on. So I will show you a different demo this time, which is a convolutional variational autoencoder. So an autoencoder, it gets the input data and tries to predict the same as it got from the input data. And on the way, it learns a feature representation of this. And what we see here is this is the MNIST data set that we saw before. So it's handwritten digits. And we see here a box of this, you know, feature representation. And what we'll do is we will select a point in this box, in this feature space, in this latent space, and it will output the image that is generated from this feature space point. And what this lets you do is lets you interpolate in feature space. Oh, that's really, really nice. So it's kind of morphing, right? But it's not morphing in pixel space, but in feature space. So this is really, really cool. And last time I have seen this in action, there was a presentation in Vienna from a guy from Zalando, and he showed like interpolation from, I believe it was a hat to shoes. And because the training set also included, a lot of clothes, it interpolated to the shoes using t-shirts and handbags in between. So it was really, really impressive to see this. And this is like a small example you can see here, but you can imagine where this is going if you use, for example, faces, or you use objects or something else than images. So there's some more. Another cool demo, so this is Keras.js, by the way, all these demos, so this is also really nice. This is an adversarial model, so you train two models, a generator and a discriminator, and the discriminator tries to identify if the image from the generator is true or not. And learning this along the way, you get a generator that you can feed with random noise for a certain class, and it outputs something that looks like that the discriminator should say that it's true. Simple example, we have here, like, we select the class 1 and we feed it with some random noise, and now we generate random looking handwritten ones. That's the idea behind it. And we can select the 3, and also we feed it with random noise, and we can create random samples. This is great actually for synthetic data sets, right? For anonymization. So that's a very nice thing. So almost towards the end. So there's also something for creating melodies, also running in the browser. There's a lot more. You find all the links in the presentation, and I strongly recommend you to go through them and to play around to see actually what is already possible today. And so I will wrap up this session with some take-home messages. Yeah, what I just said, you can do a lot of really, really great things already today. Either using pre-trained models, right, for a certain task, or you train the models in the browser. So depending on, what stage the prototype is, you can do a different thing. Everything works on image, audio, and text. I mostly showed images because it's visually more appealing, I must say. You should really keep an eye on the model size. 30 megabyte model, that's on the limit, I would say, to play around with. Everything, bigger than that is unusable almost. I mean, it still works, right? So, but you don't want to download this model in the browser all the time. And if it's possible, you should use GPU acceleration, which is, available on many devices. Yeah, and then I have one last thing to say. I think you already got it. I think it's very, very exciting today, what is possible. And I think it's a super exciting time for JavaScript developers. Why is this? Because, you see all this AI and deep learning stuff emerging. You see all these cool demos, working on a lab setup or somewhere. But really, the JavaScript developers, they write software for the browser, right? And the browser, it makes technology accessible. So you can bring all this cool, fancy stuff, all this technology you can bring to all the people around the world on every device. And that was really fascinating me. So I say thank you, and if you have any questions, I will be happy to answer.